Okay, so I guess why don't we get started here? So my name is Melissa Young. I am from Kennedy Space Center. I'm on the engineering analysis branch as a thermal engineer. We've got two other session chairs for some of our passive thermal topics. Evan and Jared, would you like to introduce yourselves?
Yeah, sure. My name's Evan Racine. I'm a thermal engineer at NASA Glenn Research Center in Cleveland. I'll let Jared go.
And I'm Jared Conjardo. I'm a lead thermal fluid analysis engineer in the engineering analysis branch at Kennedy.
Again, my name is Eric Markvicka. I'm an assistant professor in the Department of Mechanical and Materials Engineering at the University of Nebraska-Lincoln, and I direct the Smart Materials and Robotics Laboratory there. Today, I'll be giving a talk on some of our recent work on lightweight liquid metal elastomer composites for passive thermal management. This work, of course, wouldn't be possible without the students in my group. The work I'll be sharing today was primarily led by graduate student Ethan Krings, and then a former undergraduate student who's Aaron Hakey, who's a first-year PhD student at Vanderbilt. So today I'll be talking about liquid metal composites, specifically eutectic gallium indium. This is a room temperature liquid metal where the bulk melting point is around 15 degrees Celsius. When it's sort of broken up into particles or droplets, this melting temperature is suppressed all the way down to negative 85 Celsius. The metal has a very low viscosity and negligible toxicity. And one of the really unique properties of this liquid metal is it actually forms a very thin oxide skin in the presence of oxygen. And it's about 3 to 5 nanometers in thickness, which ultimately allows the metal to be molded and shaped. And you can see sort of a high-speed video on the right of the droplet of this liquid metal being dropped on the table and the sort of spontaneous formation of this oxide skin as it begins to wrinkle after hitting the table. This oxide skin allows the metal to be dispensed from a syringe and then patterned into different shapes. So here we're drawing liquid conductors connected to a light emitting diode. We can then apply current through these traces to then begin to light the LED. Right? The oxide skin, which ultimately allows or enables the formation of these traces without allowing that liquid to sort of spread through. We are focused on encapsulating this liquid metal into an elastomer composite. And we do this by mixing some volume ratio of the liquid metal plus elastomer. We combine this in a centrifugal mixer. And what we get out of this is this formation of droplets within the composite. And they're independent droplets, as you can see in the nano CT scan on the right, as you have no droplet-droplet interaction. So even at very high volume loadings, up to 80% by volume, we actually are able to create composites that are electrically insulating. And this is important, especially if we talk about potentially thermally conductive elastomers. In some cases, we want these to be electrically insulating. And so here is a graph that shows the thermal conductivity of these composites as a function of the volume loading of the liquid metal in the composite. And we see sort of an increase as the loading of liquid metal increases from 0 to 50% by volume. One really unique aspect of this is we see a negligible change in its modulus as a function of loading all the way up to 50% while remaining very highly elastic, having strains up to 600% before break. Due to the liquid phase nature of the filler, the liquid metal droplets actually deform along with the elastomer matrix as a function of stretch. So here, the top image, you see spherical droplets in the elastomer matrix. At the bottom image, at 400% strain, you see long needle-like inclusions. And if we were to measure the thermal conductivity in the direction of strain, we actually see a significant increase as compared to the base elastomer matrix. So this increase in thermal conductivity actually begins to approach some rigid metals, such as stainless steel. And this is ultimately a 50x increase over the original host elastomer composite that is strained up to 50%. So it's a pretty unique combination of properties. This material is soft and rubbery, but then exhibits some properties only really seen in rigid metals, such as very high thermal conductivity is approaching 10 watts per meter Kelvin. And this is really where sort of the first project that I'll talk about today comes in, lightweight liquid metal elastomer composites. This work, again, was led by a graduate student in my lab, Ethan Krings, in collaboration with two other groups at the University of Nebraska-Lincoln, led by Jeffrey Shield and Shinjin Ryu. And so what I've shown up to this part is usually to get these highly functional properties, these elastomer composites are typically loaded up to really high volumes, up to 50% by volume, or greater than 85% weight of the liquid metal. And this large mismatch in the density of the elastomer and the liquid metal filler is then really problematic to weight-sensitive applications, such as aerospace, and also large area electronics and thermal management. So in this project, we began to really try to understand and uncover the influence of the properties of the filler on the ultimate properties of the composite. And so here we're looking at the density of the particle filler on the left as a function of the loading of this particle filling elastomer matrix. The color map then describes the density of the composite. And what we see here, and sort of as expected, as the density of the particle filler increases and the volume loading of that particle filler increases, the density of the composite increases. If we look at the thermal conductivity of the particle filler, then as a function of the volume loading of this particle filler in the composite, where the color map then shows the thermal conductivity of the composite, we see sort of a different trend. We really see a major increase in the composite thermal conductivity only as we increase the volume loading of this filler within the elastomer matrix. And we see nearly constant thermal conductivity after some degree, after some level of sort of thermal conductivity of that particle filler. And so really to sort of conclude this, we see that, right, the density of the particle filler is sort of proportional to the density of the composite, which is as expected. We also know that the density of the particle filler is really proportional to the thermal conductivity of that particle filler. But sort of counterintuitively, the thermal conductivity of the particle filler is not proportional to the thermal conductivity of the composite and remains nearly constant above some level. And so from this, we can see that if we decrease the density of the particle filler, we'll decrease the density of our composite, where if we decrease the density or decrease the thermal conductivity of our particle filler, we'll actually see a negligible change in the thermal conductivity of our composite. And this offers us sort of a new design space where we begin to optimize not only the functional properties of these composites, but also the density. And so to do this, what we've done is we've introduced a secondary phase into this composite. So now we're introducing a low density phase into our liquid metal filler. This mixture is then loaded into the elastomer as before. And from the theoretical prediction, what we can see is so the top graph then shows the density of the composite, the bottom shows the thermal conductivity of composite, then as a function of this multi-phase loading within the elastomer. And what we see as we increase the volume loading of these low density spheres within the liquid metal, we see an approximately 35% decrease in the density as we load them up to 50% by volume, and only a 14% decrease in its thermal conductivity. This sort of nonlinear relationship then allows us to independently tune the density or thermal conductivity or the functional properties of this composite. Importantly, as the loading of this low density phase is increased into the liquid metal from 0 at the left to 50% by volume on the right, we see a change in its sort of moldability, which sort of shows up in a change in viscosity of the filler. However, we see sort of negligible changes as we begin to look at the stiffness or modulus of the composite at 50% by volume of this multi-phase filler in the composite. Finally, we can create sort of a design map from this. So we see that the volume loading of the low density phase on the y-axis within the multi-phase filler. And then on the x-axis, we have then the loading of this multi-phase filler into our elastomer composite The color map then shows this ratio of the thermal conductivity of the composite to the density of the composite. And on top of this, we can sort of draw lines then of constant thermal conductivity, shown in black, or lines of constant density, shown in white. And this really opens up a very large design space, right? The addition of this low density filler adds this design space from sort of the x-axis of this plot. So we add a bunch of sort of freedom and sort of tunability into this composite by adding sort of a second phase to our liquid metal filler. From this, we experimentally verified this theoretical model. So our red line here is then a line of constant density, where we're able to then tune the thermal conductivity independent of the density of the composite. The blue line then shows a line of constant thermal conductivity. So here we can maintain our thermal conductivity, but change its density for our application. So here our goal is really to decrease its density. The images on the right then show these three samples suspended within a column of heavy liquid, where we have samples that are able to float in this column, ones that sink, and then sort of ones that are sort of suspended in the middle. The image on the right then shows each of these materials pulled out of the liquid and then used as a thermal heat spreader, where there's a resistive heater embedded within each of these, and we see a very similar thermal response to this applied heat load. So this sort of verifies that we're able to independently tune the thermal conductivity and density of these composites by introducing a new phase into the liquid metal. Again, I'd like to acknowledge the authors on this work and also our funding support through NASA Nebraska Space Grant and the Nebraska Tobacco Biomedical Research Development Fund. The next aspect of this work is really leaning towards additive manufacturing to enable spatial control of the microstructure of these liquid metal droplets within the elastomer composite. This is a project that was in collaboration with Michael Bartlett's group from Virginia Tech, and this work was led by Aaron Hakey from my group and then Ravi Tatuka from Michael Bartlett's group at Virginia Tech. And so with this, we are also interested in being able to sort of increase and sort of tailor the thermal conductivity of these composites. And really at this point, we have two knobs to be able to do that, right? We can increase the loading of the liquid metal within the elastomer composite to see an increase in its thermal conductivity. We can also increase the aspect ratio of the liquid metal filler within the composite, and we'll see an increase in its thermal conductivity in the direction of that change in aspect ratio. However, at this point, the only way we can actually achieve a change in aspect ratio is through mechanical stretching, right? And this ultimately leads to only programmability in a single axis. However, we see that controlling droplet microstructure would ultimately enable highly tunable functional response and enhance the material properties if we were to able to spatially control that throughout an elastomer composite. Through looking at literature, we see that alignment can be caused by shear forces during direct ink writing if the ink includes these high aspect ratio fillers. We see that these fillers align as they move through the nozzle. If we print the elastomer sort of composite as an emulsion, so this is liquid metal droplets within a prepolymer matrix, we see almost no visible change of the microstructure of the liquid metal droplets before and after printing. And even looking at sort of a zoomed in microscope image of the nozzle as the material is being extruded out, we see primarily spherical droplets throughout sort of the length of the nozzle before and after extrusion. Here we sort of hypothesize, though, that solid liquid emulsions offer new opportunities to not only control the orientation of particle fillers, but also the shape of the liquid inclusions during direct ink writing. So for this, we did sort of a parameter sweep, and we looked at two specific parameters: the non-dimensionalized printhead velocity, this is the ratio of the printhead speed to the extrusion speed, and then also the nozzle height with respect to the print bed. And from this, we observed a change in aspect ratio as V star, this normalized velocity, is increased from 1 to 12. And we also saw an increase in aspect ratio as the height of the nozzle with respect to the print bed is then decreased from 250 microns all the way to 20 microns. From 16 independent experiments of velocity and height, we were then able to formulate this design map where generally we see as print speed on the y-axis is increased and printing height on the x-axis is decreased, we see an increase in the aspect ratio of these liquid metal fillers, which is shown sort of as a color map here. With this, we are able to then spatially control the microstructure throughout each sort of filament that is printed within the structure. And here we see on the left hand primarily spherical microstructures all the way to needle-like microstructures on the right in about a distance of 13 millimeters. So we're very quickly able to sort of change the aspect ratio of these particle fillers throughout a printed part. And with this, we are not only able to change from spherical to elongated droplets, but we can actually go back and create connected networks from any of these microstructures within the materials. And this is really enabling in the fact that we are able to use a single ink, one nozzle, and then achieve multiple properties throughout a printed part with spatial control. And we can begin to do sort of unique architectures that have never been shown before. It's really not possible with previous methods, such as sort of curvilinear type architectures throughout a printed part. We can alternate within a single part between spherical and elongated droplets right next to each other. We can start to print thermal messages. So here we have highly elongated droplets as shown as the in here surrounded by spherical droplets. This allows us to sort of decode a thermal message or even a heat spreader within a material. We can expand this upon 2D to 3D structures where we can begin to tailor the printing parameters, the normalized velocity as a function and printing height for each layer in our composite. This allows us to create layers with spherical droplets on the bottom all the way to highly elongated inclusions on the top of this prismatic triangle. We can add other print heads to our 3D printer, and now we can do multi-material printing, so we can embed highly thermally conductive heat sinks within sort of traditional elastomeric materials. And sort of as expected, we see significant reduction in the heat around the light emitting diodes that are located in the bottom left and top right corner of this, where these heat sinks are really embedded, or heat spreaders are embedded within the material, where we see buildup of heat where the elastomer composite remains. Again, I'd like to acknowledge the authors of this work and then also our funding support from NSF, DARPA, NASA Nebraska Space Grant, and the Nebraska Tobacco Settlement Biomedical Research Development Fund. And I'd be happy to take any questions.
Hey, Melissa, I maybe have a question just to get the ball rolling here. Eric, this is pretty interesting stuff here. But I just wanted to see, from your perspective, what sort of applications. I had a number in mind that that I could see this being, a potential use for, maybe a space application, something like you mentioned, a heat spreader and things like that, where you can, finely tune, something that's, pulling heat away from a printed circuit board and kind of control the thermal conductivity there. But did you guys have some applications in mind or some things that you're already looking at?
Yeah, we sort of envision this material could be used as sort of, I think, as you mentioned, right, conformal coatings within circuit boards. These could be sort of complex geometries between mating parts that are currently potentially sort of thermally insulating materials. Now we'll be able to, right, potentially pull heat away while remaining electrically insulating. And then I think anything that interfaces with the human body, so potentially like liquid cooling garments, things of that nature that require mechanical sort of conformability, but require sort of highly functional properties.
Oh, nice. Have you done any mechanical testing on this? Just sort of a side question, I guess.
Yeah, we have. I realize I didn't include a ton of that data. I guess there's a little bit here on sort of the bottom right. So we've done some sort of tensile stress versus strain plots and sort of measured its elastic modulus as a function of loading. But I mean, these composites are generally very, very soft and compliant.
So just out of curiosity, I guess, how long has your team, and I guess all the teams you're working with, how long has this research been going on to develop it as far as it has?
Yeah, so I've been at the University of Nebraska-Lincoln for about 3.5 years. These projects are, 2 to 3 years in length. Yeah, with sort of COVID thrown in there, so it's been
Oh, yeah,
yep.
that's amazing that what you've done in such a short amount of time still, even with a pandemic going on.
Yeah. Thank you.
Well, it looks like we do have a question from Susan Jansen. How does changing the aspect ratio of the liquid metal influence the strength of the material? Can you bias the mechanical performance?
Yeah, that's a really great question. That's actually something we're sort of studying right now that actually hasn't been studied in literature yet. So understanding how sort of the modulus of these materials change as a function of its microstructure. Up to this point, we see very little changes. They're almost undetectable on some scale, and we are really trying to understand if these changes in our modulus are a function of the printing and sort of the potentially changes in chain alignment of the polymer, or actually a function of the microstructure of the liquid metal.
Okay, and then another one that Susan asks is, does the liquid metal influence an EMI shielding capability of the elastomeric polymer?
Yes, you'll get. This isn't something we've studied, but has been shown in literature that you will get sort of an increase in EMI shielding performance as sort of the loading of liquid metal is increased.
Is there leakage of the liquid metal out of the elastomer matrix?
Yeah, so there is negligible, almost no liquid metal leakage out of the elastomer matrix. One of the really unique aspects of the liquid metal is that even if a droplet were to sort of be fractured, the spontaneous formation of the oxide skin prevents it from leaking out.
Okay.
And that's sort of analogous to this, where the oxide skin almost spontaneously forms and really prevents flow of the metal.
Yeah.
If you make the droplets then really small, somewhere around a micron or smaller, it's then almost it becomes really, really difficult to even cut through a droplet. So there are a number of techniques to be able to, ultimately prevent that from happening.
Okay. That makes sense. Oh, we've got a few more questions that just popped up. Can you orient the liquid metal needles perpendicular to the print plane for enhanced thermal pads or limited to the in-plane direction?
Yeah, that's a really good question. So currently our direct ink writing setup, it's primarily limited to the plane. You can think about potentially creating a very tall, slender structure. While that might be difficult, you could then sort of orientate it perpendicular to the plane. There's been other research and literature that has integrated sort of ferromagnetic particles into the liquid metal. You can then cure the composite within a magnetic field to then orientate sort of with respect the in-plane direction. But I would say our direct ink writing process as is primarily limited to in-plane.
Yeah, okay. And I think we have one more question related to the last one. asking, can the liquid metal then like reseal itself in a vacuum environment?
Yeah, so that's a really good question. I assume this is sort of related to the formation of the oxide skin. So the oxide skin forms in the presence of minimal oxygen. So we have some collaborators at the Air Force Research Laboratory that have sort of a state-of-the-art glove box where they've tried to minimize the amount of oxygen in there, and they still get the formation of the oxide skin on the liquid metal. And there's been some studies that have shown even as small as like 10 parts per million oxygen can cause the formation of the oxide skin on these liquid metals. And in addition, the dissolved oxygen in sort of the elastomer or whatever other materials you're using is more than sufficient to sort of form the oxide skin on these droplets. So it requires very, very, very little oxygen.
Okay, so have you tried to test it in like a vacuum chamber?
We have not, but it'd be interesting. We'd be excited to potentially collaborate with someone to do such a thing.
Yeah, that'd be interesting. That'd be neat. I guess another question, rough estimate of the range of orthotropic thermal conductivity ratios. Do you have a rough estimate?
Yeah, I had a graph in here, but it looks like I didn't include it. But yeah, so we see a pretty significant increase in the direction of strain of the thermal conductivity. In the perpendicular direction, sort of in X and Z, then we see almost a negligible change in its thermal conductivity. We see almost no decrease. While very slightly, it remains almost nearly constant.
Okay, another question. This is from Sean Breeding. Do the droplets have a pore pressure? If so, how does the elastomer behave when subjected to the vacuum environment? Would it swell in the thickness?
That is a really good question. I don't think they have a pore pressure, but I would assume they wouldn't, but I don't know. I haven't thought about that enough. Yeah, I mean, we've definitely put them in like desiccators and stuff under not crazy vacuums, and they don't necessarily they don't swell or sort of begin to leak out or anything like that, and that we've been able to sort of visually observe, but we've never looked at this on sort of a microscopic level.
Curious about the biocompatibility of the liquid metal elastomer, considering the mentioned application before.
Yeah, really great question. So the bulk liquid metal has negligible toxicity, but it is a skin irritant. But once it's sort of encapsulated within the elastomer matrix, traditionally sort of like a silicone elastomer, then it's sort of compatible with the human body. And compatible with potentially other materials, right? Gallium is highly reactive and will react with most metals. So once it's sort of encapsulated, it's sort of safe around all kinds of different metals and the human body. And even as if you were to even create sort of independent droplets of liquid metal, that oxide skin generally will prevent sort of interaction with other metals as well. That's sort of been demonstrated in literature.
Okay. And then another question, does the liquid metal have a max allowable temperature? And does that differ from the elastomer?
Yeah, that's a really great question. So the max temperature of some of the polymers we're using are a few hundred degrees Celsius, probably 250 to 300 degrees Celsius. The max temperature of the liquid metal is then sort of in the thousands of degrees Celsius. So it's beyond most of the polymers that we use. One of the sort of really critical temperatures is then actually the minimum. So when does it transition from liquid to a solid? In its bulk state, its melting temperature is around 15 degrees Celsius. But if we sort of begin to put this into particles, we get a supercooling effect, which then suppresses this to negative 85 Celsius, which is sort of around or sort of after the limits of most of these elastomer matrices that we're currently using, where we get a large increase in stiffness from the silicone before we do the change from liquid to solid state.